Hi everyone. So I'm Chen Zhang from National University of Singapore. So I will present our work on reference-free multidimensional automatic dialog evaluation. So next. So here is an outline of my presentation. So next. So for the research problems, we identify two problems. And so we try to design a framework to tackle them. So for the first problem is that nowadays there are many existing dialog evaluation metrics that heavily rely on human written references, such as the word overlap metrics like view, meteor, and all those embedding-based metrics. As we all know, all these human written references are quite expensive to obtain. So secondly, when humans try to evaluate a dialog, they try to look into multiple dimensions so as to get a holistic impression of the overall quality of the dialogue. So we have identified several of the aspects. For example, the language fluency, which means the syntactic quality of the response generated by the dialogue model. The contextual relevance, which means that given the dialogue history with a response is appropriateness to the context, and also the semantic appropriateness, which means that whether the response is the dialogue is topically coherent. As the fourth aspect is the logical consistency as well as the engagingness. So in light of the two research problems, we try to propose a reference-free automatic dialogue evaluation framework that is able to evaluate the dialogue along different dimensions. So we propose a RME framework. So what is RME? It is a reference. RME refers to a reference-free multi-dimensional evaluation framework. So it is a multi-task model that relies on self-supervised learning. So the training of the model is purely on the human-human conversations, and we try to evaluate on the human chatbot dataset. So the overall framework consists of 4 components. One is a shared encoder, which is a master language model, and we have identified 3 relevant tasks. One is the utterance type prediction task. So it's a task that rely on negative sampling strategies to tell the model what is a good dialogue and what is a bad dialogue. So basically, given the context, we try to predict whether the response is a original response within the human-human conversation, whether it is has been swapped with one of the context response utterance, and whether it is a generic response, such as I don't know or hello, or whether it is a response that is randomly sampled from another conversation. So the second task we identify to help with evaluation is a natural language inference task. So we're all quite familiar with this. So it's a 3-way classification to identify a pair between the context and the response to identify the relationship, whether they entail or they contradict each other, or whether they are neutral pairs. So the third task we identify is the simplified mnemonic entity recognition task. The reason why it's simplified is because we just try to detect the entities within the utterances when there is no type attached to it, no entity type. So it's only a sequence labeling task by assigning a BIO label to each of the token. So with this framework, we try to evaluate 4 dimensions. They are language fluency, logical consistency, semantic appropriateness, and context relevance. So I will go through each of the tasks or architecture of the task in detail. So for the utterance type prediction, here you can see here the input is the previous context, the current response, and the succeeding context. So for the then we concatenate the previous context and the current response. We also concatenate the current response and the succeeding context to form 2 sequences. Then we pass through the Robota encoder and get 2 sequences of embedding, and then pass them through a VSM layer and use the hidden state corresponding to each of the sequence and the matching feature. And after that, use MLP to do a 4-way classification. So we obtain a probability distribution. So P0 corresponding to the original class, P1 is a swap, class P2 is a generic, and P3 is the random. So here's the architecture for the utterance type prediction. So next, here is natural language inference task, you can see that the low-level encoder and the input is similar, but only the head is different. So after the encoder, we use the first token, the embedding corresponding to the CLS token of each of the two sequences to do a theory classification. So the first probability distribution try to describe a relationship between the previous context and the current response. The second one is corresponding to the relationship between the current response and the succeeding response, a succeeding context. Yeah, next. So the third task is simplify the name entity recognition task. So the low level is similar here. So after the only difference is that we concatenate all the context and response into one single sequence and pass them through the encoder, the BISTM layer, and CRF layer, and we assign a BIO label to each of the token. So it's a simple sequence labeling task. Yeah, next. So for our experiment, we try to do two types of evaluation. So one is the in-domain evaluation. So another one is the out-of-domain evaluation. So for one model, we trained with a personal chat dataset, and we evaluate on the personal chat log dataset. So we can see that these two datasets are of the same domain. And another model, we trained with a daily dialogue, the combination of daily dialogue and the movie dig. And we try to evaluate on the watch and DBDC human chatbot dataset. So for the personal chat log evaluation dataset, they perform human evaluation along 8 dimensions, which include interestedness, avoid repetition, and engagingness, and so on. So in the dataset, there are total 29 dialogue system configurations, and in total 3,316 test cases. So for the watch and DBDC, it's kind of similar, but the difference is that instead of dialogue level annotation, they give turn level validity annotation. So for each annotator, we annotate utterance whether it is valid utterance or acceptable utterance or invalid, given the dialogue history. So in order to compute the correlation between our model score and the validity score, so we try to obtain a single turn level score by taking the weighted average of the above 3 scores. Yeah, next. So here we can see the experimental result. Here is the Spearman correlation between the score generated by our model and the score, the human scores. So the first 4 columns are adapted from the 2020 ACL paper. So the MODI is one of the framework they propose. So we can see RME quite outperformed them by a quite number of a large margin. So except the inquisitiveness. So we should note that this one is a calibrated correlation with on the system level. So that's why it's quite high here. So next. So here we show the Spearman correlation with the raw score across the 3,000 plus test cases. As we can see, the purple color corresponds to the RME framework. You can see across almost all of the categories, it is the longest. But we can see the correlation, the scale is 0.1, then the correlation is lower. Like almost all of them are around 0.2 plus as compared to the system level correlation. So this one is on the dialogue level, so it may be lower, but they outperform all the baselines. So yeah, next. So let's look at examples. So I want you to focus attention on the utterance generated by model. I'm a big fan of American sports. We can look at the previous sentence. The human says, I love animals. They are better than humans. And the succeeding sentence is, I love the NFL. So here we can see there is the model is not not answering the previous. It's not appropriate within this context. So the model is giving the evaluation model gives a very low score to this sequence to this utterance. Yeah, next. Here we actually show the result on the for the out of domain correlation analysis. Here is the result for the WorldChat dataset. So we can see the rate value are adapted from the IWSDS 2018 paper. So this is the only paper I found that did the same thing as me, as us. So we can see, we can focus the result on the first 3 rows. So for the top, Juka and Iris, as we can see, our result is lower than their correlation. This is because their model is directly trained on the WorldChat dataset, WorldChat training set, and evaluate on the WorldChat test set. But our model is trained on totally different domain, human-human conversations. So this may explain the lower result here, but we will explore more by enlarge the data set maybe, and also explore more better learning strategies to improve the result here. Next. So here it shows the result for the DBDC correlation. As you can see, the correlation here is also not very high, it's around 0.2. But we need to notice that this is across the 8,509 data points. So it's quite a lot. As we can compare, which consists of 3,316 data points. The correlation is also 0.2 plus. So here we can see the result may not be as bad as what we think. Yeah, next. So for the future work, we would like to firstly identify some more new tasks that are relevant to different evaluation dimensions, such as grounding on knowledge and personal profile, which, for example, in order to consider the engaginess of a dialogue, the human may think that the dialogue agent is, when the dialogue agent is knowledgeable, then the conversation may be interesting. So we would like to propose more subtasks along that line. And secondly, as we all know, the multitask learning framework are quite hard to train. So the number of subtasks increase, so we need more effective MTL training strategies. Now we just combine all the losses. So for the third point, we want to improve the automatic labeling process by exploring more effective self-supervised or semi-supervised learning strategies. Because, for example, for the utterance type prediction task, we guess that the random sampling, negative sampling strategy may not be enough to tell the model what is the bad distribution corresponding to what are the bad dialogues. Maybe, for example, we need to tell the model what type of dialogue is not interesting, not engaging. So because the whole point is to rely on self-supervised learning, so we need to explore all these negative samples. In addition, for the natural language inference task, we also rely on automatic labeling, because as the number of training data increase, the manual labeling process will become quite cumbersome. So we need to explore more effective self-supervised or semi-supervised strategies to do the NLI labeling process. Yeah, that's all from my part. Yeah, here are the list of references. Thank you.
So are there any questions? I see one from Tim Anderson.
Yeah, all of these databases were text databases, is that correct?
Yeah, all text.
So what do you think the effect is of now if you do speech input to derive those? Rather, you think your performance will drop dramatically?
Sorry, firstly, I'm not quite familiar with speech, but I will try my best to answer your question. Maybe if you input speech, first we need to we need an ASR module, right, to transcribe the audio into text. Then we apply our model on that. If you want to directly train a model with speech, maybe I need to do more research on that.
So, I mean, basically the question is how robust is the performance to errors? Because with speech, you'll get a lot more errors in the text.
You mean input speech, how robust is the model?
I would say, just again to butt in, my experience with the kind of recognition ASR that's provided by, let's say, Amazon, or I've been reminded to show my beautiful visage. What is the case is that the current state of the art in available online or cloud recognition from Google or Amazon is really pretty good. In our experience, with quite a lot of conversational data in the Amazon environment, yes, there are errors, but they're surprisingly few. At least to somebody who's been around this speech recognition stuff for a long time. I would say that you can do pretty well.
For me, this is an interesting research area because if you remember the end-to-end, we are moving into this kind of systems, and probably we can try later to see the performance on the speech recognition system over the evaluation. But in general, I will expect more natural or more fluent sentences when you speak directly to the system rather than typing. But I don't think this will be having a big drop in the performance. I think probably a little bit based on speech recognition errors. But in general, I think if the transcription is good, basically the meaning of the sentence and the contextuality with the previous sentence and next turns should be kept in the system.
Thank you.
Great. So we're actually kind of lagging a little bit on time. Somebody has a really great question, well, that they think is great. Please pose it now, or we'll just move on. Okay, let's move on to our next presentation.